इधर भी आप लोग सब पीछे वाले इधर सामने होगा, लैपटॉप बंद करो इधर सामने। Those who are sitting back side, please come. आइए आइए। सामने एक रो नहीं सामने आना और सामने आना। आपको इधर आगे ये सब खाली है ना, वो खाली है, ये खाली है। आप लोग तो पीछे जाते जा रहे हैं, इतना मोटिवेशन नहीं आ जाएगा। और प्लीज फर्स्ट फाइनल हो जाए तो अपने आप मोटिवेशन आ जाएगा। I don't know how many of you have seen the material which we have covered in the book. Have you seen?
Yes, sir.
How many chapters we have completed?
6.
I think 6 or 7 chapters we have completed. So don't be in a wrong impression that we are not moving. We are doing. Okay. So please buy book. If you don't want to buy a book, then get a Xerox copy. But that Xerox has to be half binded. Okay. I don't want it to have a spiral binding, because otherwise you put some other, Xerox copy in between. Hard binding means you will not be able to see, I will be able to find out what is there inside. Correct? So hard binded book, or otherwise you buy a hard copy from the Amazon. Okay. If you don't want it to buy it or don't want it to Xerox it, get it from here. Alright? I don't know whether you are getting this subject or not. This subject is slightly, odd man out in chemical engineering curriculum. Isn't it? It's not like the usual chemical engineering subject. You will see that it has bins of mathematics. You will have some other material from other subjects like reactor engineering, mass transfer, heat transfer. Isn't it? Okay. So we started this particular course with the discussion on why process control is required. Isn't it? That was the first question we have posed ourselves. Why process control is required? Why this subject is even a part of chemical engineering or process engineering? Isn't it? Correct. We said that typically the chemical processes are dynamic in nature. Dynamic in nature means the disturbances will keep on coming in the system, and because of these disturbances your system is going to mess up all the time. Isn't it? Correct. And as an engineer your objective is to have your output exactly at the same value. Exactly at the same value. For instance, if you are trying to produce some product in a reactor, you definitely wanted to have the concentration of the product coming out from your reactors at a desired value. You definitely wanted to have a desired flow rate coming out from your reactor. Isn't it? Correct? So the first objective for which the chemical process control is used primarily is to suppress the effect of disturbances on the control variable. That is the first objective for which the process control is called. Then the next thing which we have discussed is we said that several processes are inherently unstable and you have no other choice but to use such unstable processes. So can we stabilize such unstable processes by using external intervention? For that you require a process control. Okay. And the third requirement which we have discussed is whenever you wanted to optimize, so ultimately unless your process is profitable, it is of no use, isn't it? So you have to make your process as much as profitable as possible, isn't it? So can we have a process control to do that? So online optimizing control, that is what is the third requirement for which the process control is called. We have also seen one case study in tutorial number 1 where we have seen how online optimizing control can be used in the actual process industry. In fact, that tutorial problem was the problem taken from the actual industry. GSFC, Gujarat State Fertilizer Corporation, they have the unit for production of nylon 6. They produce around 10,000 kg of caprolactam. They dump in the reactor and they produce nylon. Nylon 6 is used for what? Making the fiber, isn't it, which is used in socks, which can be used in fishing nets, isn't it? Also, nylon 6 sometimes used in. So I don't know, nowadays there are, everybody is having the digital watches, isn't it? Earlier they used to have different type of, analog type of watches. So inside that you will see the gears inside the watch. Those are made up of nylon. Alright. So that is the first tutorial we have seen. Then we said, okay, requirement is okay, isn't it? But how we can, start? So in order to start with the process control, definitely we wanted to know the process well, and that is where we started looking at the model. And when we say the models are nothing but what? Models are nothing but the balance equations. Whether it is a mass balance, energy balance, component balance, or in sometimes momentum balance. Out of these 4 balance equations, the balance equations which are used in process control is primarily mass balance, energy balance and component balance. Momentum balance we don't use that frequently. Momentum balance we have already seen in the subject like fluctuation. Okay. Another aspect of the model is typically when you wanted to design the control system, you do not have your experimental setup available with you. That is what typically happens when you are designing the big plants. All the EPC companies, they design the entire plant including the control system, isn't it? So they do not have a choice of doing the experiments. So in such cases, the knowledge of the process you can extract only by using mathematical equations, and that is where the model comes into the picture, isn't it? Clear? So the second question which we started looking at is why model? Why model? Because we wanted to know our system well. That is why the model, isn't it? Unless or until you know your system well, you will not be able to add any external intervention in the process. And that is the reason why model is required. Okay. Then we again move to another question. Okay, we started with why process control required. Then we gone to the another question why model is required. Then we ask another question. Okay, model is there. Requirement is also known to us, isn't it? What else is required for process control, isn't it? So we say that okay, if you know what is the process, if you know the model, based on the process and the model, we will be enumerating what are the input variables, what are the output variables. Out of the input variables and output variables, input variables we can find out what are the disturbance variables and what are the manipulative variables. So disturbance variables are those variables which you have no control on. You will not be able to do anything with those variables, isn't it? However, the manipulated variables are those input variables which you can change at your own discretion. Okay. So you have answered the third question, how you can go ahead with model and the requirements which you have specified, isn't it? So once you know your variables, what are the input variables in which you can segregate the disturbance variables and manipulated variables, and also in output variables you can segregate them as measured output variables and unmeasured output variables. So sometimes some of the variables you can measure easily. Typical example is temperature, height of the liquid in the tank, pressure inside the tank, all these variables can be measured easily. But when you talk about measuring the concentration inside the reactor or inside the tank, it is not easy to measure. When I am saying easy to measure, I am actually talking about how much time it takes to measure. Okay, temperature you can measure quickly, but you will not be able to measure the concentration quickly, isn't it? And this time is extremely important in process control. Why? Because whenever something messes up in your reactor, you have to act on that immediately. If you are, let's say, process engineer, if something messes in your plant and let's say you are in charge of that plant facility, you have to decide immediately what to be done. Isn't it? Correct. So your external intervention depends on the values of measured control variables, isn't it? Sometimes some of the control variables are not measurable, even their values you require, and very often we get the information about such unmeasured variables by using the indirect measurement. A typical example is we can measure the concentration inside coming out from the distillate by using the temperature of top 2 to 3 trays in the distillation column. Okay, and that is what typically people use in the actual process industry. They don't measure the concentration of the distillate, they rather measure the temperature of different trays, and then they predict what is the concentration. Okay, so measuring the temperature is quick compared to measuring the concentration. Alright. Okay, now you have done the measurement, isn't it? Third question is also answered, you have done the measurement. The next question is how this information which you have gathered is used for adding the external intervention. Whether your external intervention should be proportional to the error obtained between the measured values of your control variable and their desired set values, isn't it? Or do you need to do something more than this? Isn't it? So how this information is actually used to perform the external intervention, that is the fourth question. Yeah. Okay. In the last class we have seen this example. It is the same example I am again doing because unless you appreciate this, later things are going to become more and more mathematical. If you don't appreciate it now, later it will be just, all will be, bouncers. I don't want it to go there unless we appreciate it now. Okay. So this is the same example which we have started with. We said Fi, Ti are the inlet variables, isn't it? Outlet variables are F and T, isn't it? My desired variables here are to maintain, my control variables here are to maintain the height of the liquid in the continuous stir tank heater, and also to maintain the temperature of the reaction mixture inside the tank to a fixed state value. For a time being, we have assumed that this Fi is not changing. This Fi is same as the outlet flow rate here, isn't it? So in that case, height of the liquid in the tank is not going to change. So only disturbance variable in that case is Pi. Since I am assuming that Fi is not changing, it's not a disturbance variable. It's no longer the disturbance. The only disturbance variable in that case is Pi. So if there is a change in Pi, how the temperature of the reaction mixture in this particular tank is going to change with respect to time. In order to find out that, we have used the model equation. So this is the model equation we had, isn't it? Where we are saying that V rho Cp dt by dt is given as F rho Cp Ti minus C plus Q. This we have already done, but I am again doing it one more time. I am doing it one more time primarily because I want you to be sure about what we are doing. Okay. All these equations and this concept we are going to use directly later. We are going to use directly. I don't want you to spend time later on explaining you the same thing which we have already done. Okay. So this is the model equation In this model equation, you can see that the output variable is t. How the output variable t is going to change if there is a change in the input variables. What are the input variables? Input variables are ti and q. And out of these two input variables, ti we have considered as disturbance variable, whereas q is a manipulated variable. Why manipulated variable? Because q you can change. You can change q. Isn't it? In this diagram you can see by manipulating this flow rate you can change q. So either I can take FSC as a manipulated variable or I can take q as a manipulated variable. Both are same. They are not independent. They are not independent. Is it clear? So this equation which we had, this equation gives me how the temperature inside the tank is going to change if there is a change in the input variable, and that input variable could be Ti or Q, both. Okay. Now Ti is not in my hand. Ti is the disturbance variable, that is not in my hand. It is coming to the system from the external environment. But Q is in my hand. So now what I am trying to make here is, I am going to change Q in such a way that whatever the effect this change in Ti is going to have on the system, I am going to negate that. I am going to negate that. Isn't it? In order to negate the effect of disturbance on the system, I am going to change this manipulated variable Q. And there comes this proportional control. Okay. So we are saying that I am going to change this Q proportional to the way this T is changed from its steady state value. So the external intervention is proportional to the error. External intervention added is proportional to the error. And such controller is called as proportional controller. Problem with the proportional controller is, whenever I have a proportional controller, I don't get zero error. I don't get the offset equals to 0. Again, this particular statement is not completely true. We will prove later. This is true only in case of first order system, second order system, third order system, etc. But if you are having a pure capacitive process, we will see what is pure capacitive process. In a pure capacitive process, even the proportional controller can give you the zero offset. And that is the reason a typical example of pure capacitive process is a level control. And this is commonly asked question in the interview. Whenever there is a level control, which controller is preferred? The answer is, whenever the level control is there, the preferred controller is proportional controller. Why? Because if you use a proportional controller for level control, you don't get offset. We will prove that later. So this graph which I am showing, this graph is true for first order process. Second order process, we will have a similar offset here, but this nature of the curve will become sigmoid. That also we will prove later. Okay. Alright. Then we said, okay, proportional controller is good, very simple, only one parameter to vary, isn't it? No complexity at all. But the only problem is it will not be able to eliminate the offset. So in order to eliminate the offset, we have designed another controller. That another controller basically makes use of integral action. What is integral action? Integral action is nothing but I am going to increase the control action as long as there is a persistent error is present. So you can see that this particular term is actually calculating what? It is calculating the area under error curve. And if the error is not becoming zero, then this particular term will keep on increasing, isn't it? Because y-axis will be error and the x-axis will be time, and if the error is not becoming zero in a given time, area under the curve will be increasing. So this particular controller has a property that it will keep on increasing your control action as long as there is a persistent error, and therefore this particular control action has a ability to eliminate your steady state error completely. And that is the reason when you are using the integral control action, there is no offset. You can see with integral controller there is no offset. But this particular control action also leads to another problem, and that another problem is what? You get oscillation. And why you get oscillation? Because this error you are calculating, what this T is actually, this T is a measured value of T, and measured value of T will not be exactly same as the actual value of T, because every measurement unit will have some time delay associated with it. So what it means? It means that you end up with applying the control action which is actually corresponding to a time a while ago, not with respect to that time. Isn't it? So you end up with applying more control action or less control action when the other is required. Okay. And that is the reason why you get the oscillations. That is the reason why you get oscillations. This is one problem with the integral control action. Another problem with the integral control action, something called as integral winding. What is integral winding? So see, what is the control action here? You are increasing the flow rate or you are decreasing the flow rate. Isn't it? But you can increase the flow rate up to some limit. You will not be able to increase the flow rate to infinity. There is a limit to the wall. Isn't it? So even though your controller is giving you a signal that you increase the control action, but there is a limitation based on the equipment you are using. Isn't it? So after some time, even though there is a control signal which is giving you a continuous increase, but in an actual real life case you will not be able to increase beyond. That particular problem is called as integral winding. We will look at it again little bit in more detail as we go ahead. Okay. So then we say, okay, this is the problem with this particular controller. Can we do better than this? So in such cases, I wanted to eliminate these oscillations. All these oscillations are happening because of what? All these oscillations are happening because the measured values of the output variable are not same as the actual values of the output variable. And in such cases, you need to have something which can anticipate your values. Isn't it? And therefore derivative control action is added. So you can see that all the proportional controller, PI controller and PID controller, there is a logical transition. They are not arbitrarily done. There is a reason why people have included this. So derivative control action is added because it has a anticipatory property. Anticipatory property in the sense that if you are here, let's say here, you can see that you can predict that your error is going to increase in the future time, isn't it? So you will be adding more control action. But let's say if you are here, you already know that your error is going to decrease because the slope is decreasing. So in that case, you are going to add the resisting effect. Why? Because if you continue with the same value of the control action, then you end up with having the oscillation. So you can see that the derivative action can add the anticipatory effect, and because of that it stabilizes your control. Alright. Then we say, okay, very simple system, perfectly alright. But typically when you are designing the control system for a big plant, you have thousands of equations. Isn't it? Enumerating the equation for a continuous surtan or a different surtan heater, it is easy, isn't it? But enumerating the number of equations in actual plant is very, very difficult. Why? Because you have thousands of equations. And some of these equations are sometimes redundant. Means you are applying the same equation in different form. So knowing the degree of freedom is very, very important here. Why? Because if you know the degree of freedom, you can pinpoint and find out how many control loops are required. And why knowing the control loops are important? Because the entire cost of your fabrication depends on that. The number of control loops you are having, those many number of measurements you require, those many numbers of controllers you require, isn't it? So your fabrication cost depends on how many control loops or how many measurements are there in the plant. Okay. And finding this information is important. So there comes this concept of degree of freedom, isn't it? So the degree of freedom is same as the number of control loops required, isn't it? You can see that in most of the cases number of equations are less than number of variables, isn't it? So whatever is the deficit between these two, those many number of control loops you are adding, and whenever you are adding one control loop, actually mathematically what it is? Mathematically it is you are adding one more equation. Okay. So when you are having the number of control loops same as what happens? I am just observing you two while please come. No, I choose to ignore for 2-3 times. But then if I see that it becomes persistent, then I have to add that integral control action. Then please sir, explain. बाहर आ जाओ. नहीं सॉरी doesn't must here man. Please come. And what you are doing in the laptop, I told switch the laptop and pay attention here. Where you are paying the attention? ये अकेडमिक्स खुला हुआ तो ये अकेडमिक्स के लिए रूम में करो ना, यहाँ पे क्या कर रहे हो? So I am, I have ignored you guys multiple times because that actually breaks my tempo. I have ignored, but it is continuously going in the same way. You please tell me if you are not interested. I will mark your attendance throughout the semester. Do not break the tempo of the class. Do not, create a problem here. I just hate this. And I will see how much you smile after these quiz. I will find out that. I have seen many people and how the smile, vanishes after the quiz that I have known. Isn't it? So please pay attention to this. It's not going to come exactly whatever it is there in the book. Sorry. Here we are. Let's come.
Last week of August.
Okay, so we have been here. We said that each control loop added will be adding one more equation, isn't it? So ultimately number of equations becomes same as number of variables. So you will get a unique solution. You will get the unique. Okay. So after this we said, okay, story is going the way we are, planned, isn't it? Requirements, model, equations, isn't it? Everything is going the way we have planned. How we can modify the information, that also we have found out, isn't it? Then we said how easy to solve these equations. Very often we have these simultaneous differential equations are there, isn't it? Sometimes these differential equations are non-linear, isn't it? We wanted to keep our focus only on linear equations. So whenever we have a non-linear equation, we wanted to linearize it. For linearization, we have used the Taylor series expansion. Okay, correct. And again, to simplify the system, we said these linear differential equations we can solve. There is no problem. We can solve. But solving linear differential equation and solving algebraic equation is much more easier compared to solving differential equation, and that is the reason why we use Laplace transform. We use Laplace transform because Laplace transform converts your differential equations into algebraic equations, and since you are looking at linear differential equations, you will be getting linear algebraic equations, and all these linear algebraic equations you can solve easily, isn't it? So this is what we have started in the last class, isn't it? We said the definition of the Laplace transform is Laplace transform of any function f of t is given as f of s. I have put bar because this f bar and f both are different. They are not same, isn't it? Their definition is given as integral 0 to infinity f of t e raised to the power minus st dt, isn't it? Then we have seen the Laplace transform of the function where two functions are added. So Laplace transform of a1 f1t plus a2 f2t, we can get the Laplace transform in such cases. We can rewrite this as a1 into f1s plus a2 into f2s, isn't it? Then some commonly used functions we have seen. We started with e raised to the power minus at. E raised to the power minus at, its Laplace transform comes around 1 upon s plus a. We have seen another function which is at, which is nothing but a ramp function. So Laplace transform of ramp function is a by s square, isn't it? Then we have seen a sin omega t. So Laplace transform of sin omega t is omega divided by s square plus omega square. Laplace transform of cos omega t is s divided by s square plus omega square. So this is what we have seen in the last class. If you look at this step function, why we are looking at these functions? Because these functions will be regularly used later. So you will see that in the stability you will be looking at whether the control system is stable when there is the input which is sinusoidal input, when there is the input which is ramp input, when there is the input which is step input, whether my system is stable or not. So in those cases we will be using the Laplace transform directly. So when I am having a step function as shown here, you can see f of t is given as a when t is greater than 0 and the time less than 0 the value of the function is 0, isn't it? So Laplace transform of step function is a by s. Then this is an interesting function which we call it a translated function. Translated functions are commonly seen in process control. Why? Because every instrument in the process control will have time delay, dead time associated. So whatever input you are giving, its impact on the system will be felt only after some time. So you have a translated function. So whenever you have a translated function like this, Laplace transform of translated function can be represented like this. So you can see that Laplace transform of f t minus cd is given as e raised to the power minus std into f of s. And this is a very interesting equation. Why? Because you can find out the Laplace transform of untranslated function and you can multiply e raised to the power minus std. That will give you the Laplace transform of translated function. And most of the process will have the time delay. So this particular term you are going to use regularly. This term you are going to use regularly. Okay. And towards the end, in the last class, we started looking at this system where we said that we are having a pulse input. Pulse input. Pulse input is at time less than 0, the value of the function is 0. Isn't it? Between time 0 to time a, the value of the function is 1 by a. And when time is greater than a, my function value becomes 0. So this is the pulse function. Again I said in the last class that this pulse function can be approximated. You can have this pulse function by combining two step functions. So if you subtract two step functions, you will be getting the pulse function. So one step function will be f1t, which is having 0 between 0 at earlier time, and at time t equals to 0 and above, you will have function equals to 1 by a. Similarly, there is another function f2t, which is having the value 0 for time less than a, and when time greater than a, the value of the function is 1 by a. If you subtract both these functions, you are going to get a pulse function. Okay. Now this second function is interesting function. Why? Because this second function is exactly same as the first function, except that it is translated by a time a. It is exactly same. It is only translated by a time a. So I can represent the second function f2t as f1t minus a. And if I represent this second function as f1t minus a, I can put it in this equation. So this first function delta a t is given as f1t minus f1t minus a, isn't it? Then I can apply the Laplace transform of this entire equation. What I am going to get is Laplace transform of f1t will be what? It will be just f1 bar s. And what will be the Laplace transform of the second term? The Laplace transform of second term will be e raised to the power minus sa into f1s, isn't it? So with that I can take 1 minus e raised to the power minus s common and f1s outside here. Isn't it? You can see that the Laplace transform of, so this f1s, f1t is what? f1t is just 0 and 1 by a. Isn't it? So what will be the Laplace transform? This is nothing but a step function of a magnitude 1 by a. Laplace transform of step function with a magnitude 1 by a is 1 by as. Isn't it? So this entire bracket will be multiplied by 1 by a. So this is the Laplace transform of step function. Now the interesting thing to note down here is I can convert this particular function to a Dirac delta function. If I take this a tends to 0, if I take this a tends to 0, in that case it becomes Dirac delta. Area under the curve will be 1, isn't it? Area under the curve will become 1 and you will have a delta function like this. So can we find out the Laplace transform of delta function? We can find out the Laplace transform of delta function by taking the limit on both the sides. Both the sides we have to take a limit. Remember, this particular function becomes a Dirac delta function only when the a tends to 0. So if I take limit a tends to 0, then this becomes Dirac delta, isn't it? Correct? So same thing is done here. So this is the Dirac delta function. We have taken a limit a tends to 0, delta a t e raised to the power minus st dt, isn't it? So this entire term, what is the Laplace transform of this entire term? We have already derived 1 minus e raised to the power minus sa divided by a and limit a tends to 0. Correct? What will be the value? I have written 1. But you can see that if I put a equals to 0, you get 0 by 0. If you put a equals to 0, you get 0 here and you get 0 here. So that becomes 0 and 0 by 0. So what you have to do is, you have to apply L'Hospital's rule and you have to differentiate this numerator and denominator with respect to a. If you do that, you will see that everything will cancel out and you will get e raised to the power minus sa. Only that term you will have, and if you put the limits here, you will get 1. Is it clear to everyone? Is it clear to everyone? Yes. Okay. Now remember earlier I said that all the differential equations we are going to have in this course will be in a derivation form. I said, remember? And I said we will come back to this particular point again by the derivation form. So we will answer that. So here again let's look at the derivative. What will be the Laplace transform of derivative? Isn't it? So Laplace transform of derivative, let's take a function dft by dt. This is the function. I wanted to find out the Laplace transform of this. Isn't it? Again I am applying the same definition of Laplace transform. So this becomes 0 to infinity dft by dt into e raised to the power minus st dt. Correct? Now in this case, so see this particular term I can take as dv and this particular term I can take u, isn't it? So when I am taking the integral of u dv, remember we have taken that earlier also, if I am not u dv. So integral by parts will be given by uv minus integral v du. So the same formula is applied here. This becomes dv and this becomes u. So what I am going to get? The first term is uv. So u is this term and v is ft. Isn't it? So e raised to the power minus st ft and the integral between 0 to infinity. That will be the first term. Second term is minus integral v du. Isn't it? So now v is this f of t is the v term and du will be what? Derivative of this term, that becomes minus s into e raised to the power minus st, isn't it? That minus will get cancelled out and you will get a plus sign here. And you will have an integral between 0 to infinity s e raised to the power minus st f of t dt. You can take this s out because the only variable in this integral is t. S is constant here. So s I can take it out. If I take s out, this entire function becomes what? f of t e raised to the power minus st dt, that is the definition of Laplace transform. So I will get s into f of t, isn't it? And how about this term? Let's look at this term. If I put infinity here, e raised to the power minus st will be 0, isn't it? And if I put 0, then it becomes f of 0 minus f of t, isn't it? So you get, after simplifying, what you get is s f of s minus f of t. Now this particular term we have obtained when we had a first order derivative. Let's say if we are having nth order derivative, we get an equation like this. If we are having nth order derivative, d raised to the power n f of t dt raised to the power n, then the Laplace transform of that will be given as s raised to the power n f of s minus s n minus 1 f of 0 minus s n minus 2. So you can see that here all these terms f of 0, f dash 0, f and this is n minus 2f derivative, isn't it? Dash 0, isn't it? So you can see that all these are the initial conditions. All these are the initial conditions, isn't it? So whenever I am finding the Laplace transform of derivative, I require an initial condition. And when I take the derivative or a differential equation in a deviation form, all these initial conditions become 0. All these initial conditions become 0. So all these conditions which are here, this becomes 0. So that is the reason why all the equations you will see in process control we represent them in a deviation form, because that simplifies our analysis here. All your initial conditions are going to become 0, right? Isn't it? Is it clear? Alright? Now let's look at another interesting Laplace transform of integral. You may ask me where this derivative is clear that all our equations are differential equations, and that is why Laplace transform of derivative is important in this course. You can ask me that why the Laplace transform of integral is important. Laplace transform of integral is important because sometimes you use PI control, where the integral control action comes in. There the Laplace transform of integral is required. So that is why we are also looking at Laplace transform of integral. So Laplace transform of integral, let's say the function I am having is integral 0 to t f of t dt, isn't it? I can apply the usual definition of the Laplace transform. So this function is taken as it is, e raised to the power minus st dt. Then we have represented this e raised to the power minus st as u, and we have represented this integral. This integral we have represented as v, isn't it? So what will be dv? What will be dv? dv will be just f of t, isn't it? dv will be f of t, and du will be minus e raised to the power st into s. That will be du, isn't it? So this is the du and this is the dv. Now this particular term is nothing but what? This particular term is nothing but, okay, so this is v and this is, remember this we have taken u, but we require here du. V du we require. So v du, if I wanted to write, so see, if I put that here, you can see that it becomes minus 1 by s 0 to infinity v du. Now integral of v du we can find out by using the same rule, integral by parts, isn't it? So that becomes vu minus u dv. Just reverse of this, isn't it? Instead of u dv we have taken v du, and then this second part we have modified, correct? So now if we solve the integral, that becomes the first term becomes vu, isn't it? And this minus 1 by s is taken common here. This is vu 0 to infinity minus integral 0 to infinity v dv u dv, isn't it? If you put all the variables which we have defined here, so we have defined as this integral, so this integral remain as it is inside into e raised to the power minus st, and the limit is between 0 to infinity, and the second term is 0 to infinity e raised to the power minus st f of t dv. Okay. Now this particular function is very interesting. Why? Put the value of infinity here. So if you put e raised to the power minus infinity, it is 0. So value of the function is 0. If you put 0, what it means? You are doing this integral between 0 to 0. So what will be the value of function f of t? It will be still 0. So in both the cases, this term becomes 0 minus 0. That's it. So only term remaining is the second term. Now in the second term, this is the standard definition of Laplace transform. So that becomes f of s. This minus sign get cancelled out with this minus sign. So you get f of s divided by s. Okay. So these are the Laplace transform of some standard functions which we are going to use later directly. Isn't it? So Laplace transform of Dirac delta function or impulse function is just 1. Laplace transform of pulse function is 1 minus e raised to the power minus sa divided by as. Isn't it? Where the magnitude of the pulse is? So height is 1 by a and width is a. So area under the curve is still 1. Okay. Then unit step function 1 by s. When f of t is c, in that case it becomes 1 by s square. When f of t is t square, then it becomes 2 factorial divided by s cube. And this is a very interesting function because this function you will be having regularly when you are having multiple roots. I will come back to this again. Okay. We will look at what I am trying to say regarding the roots, that we will come back. Okay. So whenever we have a multiple roots, you will see this term. And remind me, we will again come back to this slide. Okay. So in this case, multiple roots. We will do that in the next class. So when I am having t raised to the power n, it becomes n factorial divided by n plus 1. When I am having e raised to the power minus alpha t, it becomes 1 upon s plus alpha. Isn't it? T and e raised to the power minus at, that becomes, so see now we have combined this function with this function. Isn't it? So in that case what we get is n factorial divided by s plus alpha raised to the power n plus 1. You can see some generalization here. You see some generalization. You don't need to derive. If you know the generalization, you can figure out what can be the Laplace transform of the given function. And the same generalization is done here also. You can see e raised to the power minus alpha t is there and sine and cos are there. So in that case we have retained the same formula as that of sine and cos, but instead of s we have taken s plus alpha. So some generalization we have already added here. So sin omega t, omega divided by s square plus omega square, cos omega t, that is s divided by s square plus omega square, sin hyperbolic omega t, that is given as s divided by s square plus omega divided by s square minus omega square, cos hyperbolic s divided by s square minus omega square, and whenever I am having e raised to the power minus alpha t multiplied by sin omega t, then it becomes omega divided by s plus a square plus omega square. Similarly for cos e raised to the power minus a cos omega t, we will have s plus a divided by s plus a square plus omega square. We are going to derive some more interesting formulas like final value theorem and initial value theorem in the next class. These are important because remember we said steady state error. What is steady state error? We wanted to find out the error at time equal to 0. Isn't it? We can find out the steady state error directly from the equation if we apply the final value. Directly. You don't have to solve it. Okay. So all these mathematical tricks you can be able to do it if you know all these concepts. Isn't it? The only drawback of this is this particular Initial value theorem and final value theorem is applicable only for closed functions. So whenever you are having the periodic functions which are not closed functions, not able to. Okay. So we stop here and we will continue from this point. Please buy book and go through all the chapters. I have also put around 100 slides in book. There are almost 300 slides we are going to cover in this course. Around 300 slides. Okay. In the lot of 100, I am going to put it in the school. Please get it from the school. And you don't have to, write here. You can, just concentrate in the class and go through the material which is supplied. Please say something is unusual.